Welcome to this lecture. In this lecture we are going to discuss some major properties and major facts and major results involving the Borel sigma field on the real line. But before we go forward, let us quickly recall what we have already seen in the previous lectures. So we started off with the basic notions of random experiments and saw the collection of events that are generated from the collection of random experiments. That collection of events will satisfy certain structures. We looked at certain collection of structures of subsets inside non-empty sets, and therefore we obtain these structures of sigma fields and fields. This involves these operations, the set theoretic operations, complementation, unions and intersections. For sigma fields we allow countable unions and countable intersections, and for fields we allow finite unions and finite intersections. We have seen many examples of sigma fields as well as fields. We have seen examples that which is a field but not a sigma field, and then afterwards we have seen constructions of sigma fields. One of the approaches was the bottom up approach, starting with the trivial sigma field and adding sets to that we obtained the sigma fields. Another approach was the generating sets approach, where we take a top down approach. So what we do is that we start off with the power set sigma field and judiciously remove certain sets and look at certain kind of intersections, and that's how we obtain the sigma fields generated by certain collections that we start off with. So this is what we have already discussed, and one of the special examples of these sigma fields generated by certain collection was the Borel sigma field on the real line. So it is the sigma field that is generated by the collection of all open sets that are in the real line. So we start this lecture and we discuss about results involving the Borel sigma field on the real line, and we will also see some extensions of these to higher dimensions and other sets. So let us move on to the slides. So let's look at the minimal sigma field again, generated by the collection of open sets on the real line. Now for simplicity of notation, we will write by script C subscript 0, which to denote the collection of open sets in the real line. Okay, so we will not repeatedly say the collection of all open sets in the real line. We will simply say C subscript 0 or script C subscript 0. And what we have already defined, or whatever the notations we have used so far, says that Borel sigma field on the real line is exactly the same as the sigma field generated by this script C0. So this is the definition. Now we consider different collections of subsets of the real line. So the first new collection that we see is denoted by script C1. So this is all the closed sets that are in the real line. Then script C2 and so on, we shall see certain special type of intervals. So what are these intervals? So again we will look at, in script C2 we are looking at open intervals, in C3 it's closed intervals, C4 left open right closed, C5 left closed right open. So in all of these you will see that the left endpoint and the right endpoint A and B could be infinity or plus infinity, but this is following the notations that at the end of the day these sets or these intervals that you consider must be within the real line. So therefore, for example, if in the closed set A to B, if A is minus infinity, then you think of it as minus infinity open to closed B. That's how you should think of it. So this notation has already been explained in the previous lecture. So now in C6 onwards we will see unbounded intervals. So one bound of the interval is either infinity or minus infinity. Okay, so this gives you four more types of intervals, and then there are two more types, which is C10, which is all compact sets in the real line, and then C11, which is our well-known field, which was shown as an example of a not a sigma field. So this is a field but not a sigma field. So how this was this defined? So this was the finite disjoint union of left open right closed intervals. So you look at intervals of the form open A to closed B, and if you have n many such intervals, if they are pairwise disjoint, take their union. That is a typical set in this field, and for the purpose of the discussion in this note, in this lecture, we will write it as C11. Okay, so we have this list of special sets or special type of sets in the real line. So this is what we are going to look at. So the first one was denoted by C subscript 0. Other ones are with indexing 1, 2, 3 onwards up to 11. So before we go forward in the definitions and other results, one of the things that I will repeat once more, that following this notation or the convention, for example in closed sets with minus infinity or plus infinity as the limits or the bounds, then you have to interpret it accordingly. So this is just to repeat so that there is no cause for confusion. These sets, whatever intervals or sets we are considering, are within the real line. So therefore plus minus infinity, these points are not within the sets that we consider. So now in our last lecture we had talked about sigma fields generated by different collections of sets, and in this regard we had proved this proposition 4. So please go back and check this from the previous lecture. But what this said was that if you have the fact that if you have two collections of sets, one is let's say script C and another is script D, then if the sigma field generated by script C contains the collection script D and vice versa, then the sigma field generated by C and D must be the same. So this is something was the statement of proposition 4 in the previous lecture, and using this we are arriving at a very important theorem, which is that all these collections of sets that we have introduced above, all of these separately generate the Borel sigma field. So for example, C1 was the collection of all closed sets. So if you generate the sigma field with all closed sets, you will again end up with the Borel sigma field. So you will not get a different collection of sets, but you will only get the same sigma field, the Borel sigma field that was originally generated by open sets. Similarly, for all this type of intervals that we have considered, you will again get the same sigma field. So this is a very, very important property of the Borel sigma field. So all these collections generate the same sigma field. Now there are several comments before we go forward and prove this. So the comments are like this. So first of all, remember that the generating sets belong to the generated sigma field. Okay, so whatever generating sets that you look at, they first of all have to belong to the at the end that sigma field that you have constructed. So therefore, as a consequence, what you can now immediately say is that if you assume that theorem 1, if you know that all these collections generate the same sigma field, you can immediately claim that all these sets that you have already considered, this type of intervals, closed sets, open sets and so on, all of these must be there in the Borel sigma field. So Borel sigma field typically constitutes of all these nice sets that you really need to look at. Later on we will see some examples of subsets of the real line which are not in the Borel sigma field, or which is not a Borel subset of the real line. We will see that. So the Borel sigma field is strictly smaller than the power set. But for all our practical purposes, we will typically work with open sets, open interval, closed sets, closed intervals, or left open, right closed intervals and so on, and all of these are included in the Borel sigma field. So that is something very much is needed. Keep it in your mind. Okay. So the next observation is that if you fix a point small x on the real line, then you have these both type of sets in the Borel sigma field. So this open interval minus infinity to x and the closed interval minus infinity to x. If you have both these sets on the Borel sigma field, then what you have immediately is that the singleton set small x can be written as the this set minus notation. This simply means that you are taking minus infinity to closed x intersected with the complement of this open interval minus infinity to small x. So you have this first set subtract the second set, which is nothing but take the first set, intersect with the complement of the second set. So that is the set minus notation which we have talked about earlier. Now it at the end it gives you only the singleton point small x or the singleton set point singleton set small x. That is therefore in the Borel sigma field following the properties of a sigma field. Okay, so you have every singleton subset of the real line is in the Borel sigma field. That's great. But then something nice happens. If you take any finite set or any countably infinite set, then you can write it as a finite union or a countable union of singleton sets. So for example, if you look at the set of all positive integers 1, 2, 3 and so on, you can write it as a union of singleton 1, singleton 2 and so on. And therefore, since you already know that these singletons are in the Borel sigma field, you already claim that all these countable sets, including the set of positive integers or the natural numbers, are in the Borel sigma field. Similarly, you will make the same comment about the set of rational numbers because this is a countable set. Now, it so happens that we have looked at many different classes of sets, C0 to C11, but most often we will use these 4 types of things. So C0, C4, C7 and C11. So let's just go back to that list or the description that was given right at the beginning of this lecture and see what are these collections. C0, C4, C7 and C11. So what are these? So let's go back. So C0, just to recall, this was the collection of all open sets. Next was C4. This was the left open right closed intervals which you have already used to construct these nice fields. You will also see them when we later discuss about distribution functions. Then what is C7? That is the left, so minus infinity to closed A. So that is the type of sets that also appear in connection with distribution functions that we shall see later on. And then C11 is that the example of the field that was not a sigma field. Okay, so this was the finite disjoint unions of left open right closed intervals. So that was the example. So let's go back and start with the proof of that theorem that all these different collections of sets generate the same sigma field. So how do you prove this? So you start with the first statement that you want to show that the collection of all open sets that generates the Borel sigma field, it will be the same sigma field if you generate it with only the closed sets. So for the closed sets, that collection we denoted it by script C subscript 1. Okay. So now applying that proposition 4 from the previous lecture, what we need to show are two-sided inclusions that closed sets are contained within the sigma field generated by open sets. But this is pretty simple to prove once you observe that closed sets are nothing but complements of open sets, and the sigma field, of course, sigma field generated by all open sets necessarily contains all its complements of the open sets. So therefore closed sets are there. Therefore script C1 is contained in script C0. Similarly, if you observe that open sets are nothing but complements of closed sets, so open sets or the collection of all open sets script C0 is contained in the sigma field generated by all closed sets. So therefore you have both sided inclusions as required, and you will immediately claim that both these sigma fields that are generated by one by the open sets and one by the all closed sets, they must match. So that gives you that connection. So let's try to go to a different one. For the simplicity, let's take a example involving the compact set. So this was C10. So C10, what was that? So this was a list of all compact sets or the collection of all compact sets in the real line. And we want to claim that the all compact sets that will generate a sigma field, but this will be the same as the Borel sigma field. So how do you prove this? How does the proof go? So you start with all compact sets. Recall that all compact sets are closed and bounded, and hence what you have is that all compact sets are contained in the collection of all closed sets in particular, and therefore all compact sets are contained in the sigma field generated by all closed sets. Fine. But given any closed set, let's take the set to be capital A, you can write it as a countable union like this. So how? You look at the interval minus n to n, take the intersection with the set A, and take the union of all possible n. Now what happens is that A intersection with minus n to n, that set, both of the sets capital A and minus n to n, that closed interval, both the sets are closed, so the intersection of that is closed. But this set is also bounded because it's contained within minus n to plus n. It's a bounded set. So A intersected with minus n to plus n, that set is closed and bounded, and hence it is a compact set. So therefore what you have actually able to write is that the original closed set capital A can be written as a countable union of compact sets. Therefore you have that all closed sets are contained in the sigma field generated by all compact sets, because sigma field generated by compact sets will contain countable unions of compact sets, and therefore all closed sets. Now you have shown that the collection of all compact sets is contained in the sigma field generated by all closed sets, and vice versa. Therefore the sigma field generated by C10 and C1 match, and since you have already shown that the sigma field generated by the compact sets is the same as sigma field generated by the closed sets, which is same as the Bodel sigma fields, that connects the connection with the compact sets. Okay, so let's now move on to a different type of sets as open intervals. So what are these again? So you look at open intervals of the form open A to open B for AB like this. Now these are all open sets. So therefore if you look at this collection of all open intervals, which is script C2, that is contained in all open sets, which is script C0, and therefore contained in the sigma field generated by all open sets. So therefore all open intervals are contained in sigma field generated by all open sets. Conversely, you can actually show that all open sets are actually can be written as some countable union of open intervals. How do you show this? So this is similar to what we have shown for the connection with the compact sets. So this will require again some argument like this. So how do you do this? So first of all, the first question is that you want to write a open set as a union of open intervals. To say that, you have to first figure out what are the open intervals within a open set. But that is easily obtained, because if you take any point small x, then you can find a open interval something like this. Let's say you don't need to get a symmetric interval, but you can actually get intervals of this form. So x minus some number epsilon 1x and x plus some number epsilon 2x. So you will get some interval containing that point small x, and that open interval should be completely contained within the set capital A. So if you take any open set and take any point within, there is an open interval containing that point small x, and the open interval must be contained in the original set A. So here these choices of epsilon 1x and epsilon 2x, so subscript is dependent on x, so therefore that's why it's explicitly written that these numbers epsilon 1 and epsilon 2 actually depend on small x. But what you can actually do, you can choose this epsilon 1 and epsilon 2, these numbers, large enough such that this interval that you obtained is the maximal such thing, is the largest such open interval that is contained in A, and also with the property that the open interval contains small x. So if you choose a point, then you of course get open intervals, but enlarge it on both sides, and you will get a maximal such open interval which is still contained in A. If you go beyond that, the open interval will go outside the set capital A. So this is, you can try to visualize. Okay, great. So in that case, what you can now try to show is that A is actually made up of this type of open intervals, where you just look at open intervals of this type that we have just obtained, but only around the rational points within the set capital A. So here the set Q denotes the set of rational numbers, and Q intersection A denotes the set of all rational numbers within the set capital A. And therefore all you look at are all the rational numbers within the set capital A, look at those intervals around the rational points smaller, take their union, that will turn out to be the whole set capital A. You can easily check this, try to work this out. But then what will happen is that since Q is countable, this above union of all rational points within the set A, that is also a countable set, and hence this above union is a countable union. Great. So therefore you have written a open set capital A as a countable union of open intervals, and hence you have the inclusion that all open sets are contained in the sigma field generated by all open intervals. And therefore you have both sided inclusion as required, and you can easily claim this equality applying proposition 4. So let's now move on to a different type of interval, one side open, one side closed. So let's take left open, right closed. So then you have to make a connection with all the type of some other generating class that you have already seen. So what you do here is that you take left open right closed interval AB, then you can write it as an intersection of these things, intersection of this type of an interval, open interval. How? So you take A but write B plus 1 over n. Now if you take the intersection of this, you can easily check that open A to closed B is exactly this countable intersections. On the other hand, if you take a open interval A to B, you can write it as a countable union of such intervals left open right closed. You can again check this. What this implies is that the sigma field generated by all open intervals, which is script C2, contains all left open right closed intervals, and all open intervals, which is the collection script C2, that is contained in the sigma field generated by all left open right closed intervals, which is C4. Therefore these two must match. But since we have already proved that the sigma field generated by only the open intervals is nothing but the Bodel sigma field, you also have that inclusion. Great. Now let's come to C7. So what was C7? C7 was intervals of the form minus infinity to small x, closed. Okay. Now of course, if you look at such intervals, they are already left open right closed, so therefore they are contained in the sigma field generated by left open right closed intervals. On the converse, if you take an interval of the form left open right closed AB, then you can write it as a set like this. So you take this infinite interval minus infinity to B, but subtract out minus infinity to A. Recall that this is nothing but the intersection between minus infinity to B and the complement of minus infinity to A closed. Okay. So therefore you get this, and therefore such sets, this left open right closed intervals, is contained within this left open right closed infinite intervals, which is the collection C7. So therefore you have this connection, this equality, and therefore from the previous results you immediately claim that these are all generating the Bodel sigma field. And finally let's come to C11. So that is our familiar field, which is not a sigma field, and this is made up of finite disjoint union of left open right closed intervals. But then these left open right closed intervals are contained in the sigma field generated by only the left open right closed intervals. That's fine, and therefore you have that inclusion. But conversely, if you look at only left open right closed intervals, they are of course contained in the collection in that field generated by this finite disjoint union of such things, and therefore you have that inclusion, C4 contained in C11. But then you immediately claim that okay fine, C4 is contained within the sigma field generated by the field C11. Therefore you have both sided inclusions as required in the proposition 4 earlier, and therefore you have the equality that the sigma field generated by C4 and the sigma field generated by C11 both must match. In a similar way, you can try to connect all the other type of sets that are left out. You can try to check this. The rest of the proof is left as exercise for you. Please check this. So you have already shown that many different classes or many different types of sets, all of these generate the same sigma field. In fact, you can also try to look at other types of special types of sets. In particular, you can look at all infinite intervals of this type with rational endpoint smaller. Okay, so again Q denotes the set of rational numbers, and choose all those intervals of the form minus infinity open to closed R. Try to check that the Bodel sigma field is generated by this collection of intervals. Okay, so you are not considering points where we are not considering points, irrational points, and we are not considering this type of sets where the right side bound, right side limit or small r is irrational. We are not considering those type of sets. We are only considering rational endpoints here, and try to see that these will in fact generate all types of sets, and that will give you the Bodel sigma field. Try to see this, try to work this out. Okay, but then we can now move on to a different type of sets, which is the Bodel sigma field on other type of sets. Now we have already looked at this generating collections on R. Now with this motivation at hand, we now look at several different sets. For example, the extended real line, which we denoted by R bar, higher dimensional Euclidean space, some RD, and some specific Bodel subsets of R. In fact, we will look at sigma fields or Bodel sigma fields on Bodel subsets. So on the Bodel subset, they are also non-empty sets. You can ask whether there are sigma fields, and we shall construct that. So let's go to the extended real line and see what is the notion of Bodel sigma fields there. So again, on the real line, we saw that there are many different types of sets that generate the sigma fields, that Bodel sigma field. And again, just taking that motivation, what we do is that we will focus our attention to these left open, right closed intervals. So take these left open, right closed intervals, open A, closed B. But here remember that we have to take, we can take the points A, B to be infinity or minus infinity. They can be like that. So in that case, what you take in the extended real line, you take this type of open intervals, left open, right closed intervals and generate a sigma field. Whatever you get, I will call that as the Bodel sigma field on the extended real line. So here again, just to repeat, the sets open A to closed B are subsets of this extended real line and therefore may include the points plus minus infinity. So you might ask, what about the usefulness of left open, right closed intervals? Why not look at other type of sets? But we shall see the usefulness later on in connection with some distribution functions when we discuss that later on. Now remember that we have also discussed a field script C, not a sigma field, on the extended real line. So that was defined earlier. You can now try to check that yes, this also generates the same sigma field, the Bodel sigma field as defined above. Okay, so we have only taken the definition of the Bodel sigma field on the extended real line as the sigma field generated by left open, right closed sets. But now we are saying take the field which is not a sigma field, that example on the extended real line, and try to see that it will also generate the same sigma field. So the arguments goes as the same argument that was done on the real line side, but it's again can be same argument will work here. Try to write it down. So now there is a very interesting observation. Let's look at the Bodel sigma field on the extended real line that we have observed. So the sets that you see there, the Bodel sets that you see on the extended real line, they may contain plus or minus infinity because these are subsets of the extended real line, but take their intersection with the real line. So this is the notation for a collection of sets. So what we mean is that one side of this intersection, you see that we are looking at a collection of sets of the collection of subsets of the extended real line, and we are intersecting that with a real line. What does it mean? It simply means that we take sets capital A and intersect with the real line. So these are all the types of sets that I am going to consider, and that is the notation that we have written, intersection with R. So that is the notation that we are introducing. Okay. Now we are saying that take Bodel sets capital A, take their intersection with the real line. Now what is happening is that if the Bodel set capital A contains plus minus infinity, you are simply removing that. It may so happen that the set capital A does not contain plus minus infinity. In that case, it's already within the real line and it will be a subset of the real line. If there is a plus or minus infinity there, you are simply removing that and taking the rest of the set. So that is the collection that we are considering now. Now there is a general principle called the principle of good sets. We can actually show that this collection that you have just talked about will exactly match with the Bodel sets on the real line, or the Bodel sigma field on the real line. So therefore what we are saying is that if you take any Bodel set on the real line, that you can write it as a intersection of a Bodel set on the extended real line intersection with the actual real line. So that's the description here. But this principle of good sets, it's a bit technical, and due to certain time constraint, we are not going to discuss this principle or this methodology in this course. This is for your information that there is some general methodology called the principle of good sets that will allow you to prove such equalities. So with that at hand, now we move forward to the Bodel sigma fields on the higher dimensions. And for simplicity, don't jump from one dimension to a very arbitrary higher dimensions. Let's go to 2 dimensions. So on dimension d equal to 2, using the ideas that discussed above, what do? We again look at left open, right closed sets, but we are now going to look at certain special type of things, rectangles. And the rectangles will be made up of such things. So you take left open, right closed interval AB and another left open, right closed interval CD, take their product. So by that I mean that I take points on the 2 dimensions whose first coordinate is lying within the set A to B, open A to closed B, and the second coordinate is lying within the set C to D. Okay, open C, closed D. So that's how these points are described. So that's kind of a rectangle that you see on the 2 dimensions. Now look at such rectangles and look at this collection, then generate a sigma field. So again, the generation of sigma fields that can be done on any non-empty set. If you have a specific collection of sets, then you can always generate a sigma field. So we are looking at this special choice of rectangles on 2 dimensions and generating a sigma field, and whatever we get, we define it as the Borel sigma field on R2. So again, the motivation is simply coming from 1 dimension. So on 1 dimension, we focused our attention to open A closed B, this type of left open right closed intervals, and the exact counterpart of that in 2 dimensions is this product type sets. More generally, if you go to higher dimensions, D dimensions, arbitrary D dimensions, all you have to look at this default product of such intervals. So by that I mean you look at intervals ai bi, so that the ith component lies within the set open ai to closed bi, and take the default product, whatever that rectangle or the cube or general set that you get in D dimensions. You look at that collection of sets, collections of cubes, D dimensional cubes, and generate a sigma field. Whatever you get, we define it as the Borel sigma field on RT. So with this motivation that we have already taken from the real line, we are extending this notion of Borel sigma fields to the extended real line and the higher arbitrary dimensional Euclidean spaces. But you can now ask, okay, we had started this lecture with different types of generating sets for the Borel sigma field on the real line, right? But you can now ask, okay, are there any other types of sets that you can consider, for example, on R2, on 2 dimensional Euclidean space? Are there other generating sets that will generate the same Borel sigma field on R2? The answer is yes. But this is possible. This again, you can take the motivation from 1 dimensional arguments and extend these notions appropriately. But in this course, again, due to time constraints, we are not going to discuss this, and again, we will not really require those other generating sets even if we go to higher dimensions. Okay, this is for your information. You can still try to work out what are other generating sets on the extended real line or the higher dimensional Euclidean spaces. And now we come to the final topic of this lecture. So we now look at Borel subsets. Let E be a Borel subset. Now E is a non-empty set. Now what we want is that we want to define a sigma field of subsets of E now, and we want to get the notion of Borel sigma fields there. And motivated by this previous notion in note 22, what we have observed there was that the Borel sigma field on the extended real line, if you take their intersection with the real line, you get back the Borel sigma field on the real line. So let's repeat. Real line was a subset of the extended real line. You have a Borel sigma field on the extended real line, the bigger set. Take intersection with the smaller sets, that is the real line. You end up with the Borel sigma field on the smaller set, the real line. So therefore, with this motivation, you can now say, okay, since E is a subset of the real line, the real line is now a bigger set. We already have a Borel sigma field on the real line. What happens to the collection of sets if you take the intersection with E? And that's this collection of sets. So we look at all Borel sets capital A, Borel sets of the real line capital A. You take their intersection with E. And you can now try to show that this intersection is this intersection is actually a sigma field on E. And just to clarify, again, whatever operations, set operations that you do here, it's within the set E. That means you take unions of sets within E. So A intersection E, this type of sets are already subsets of E. So if you take unions and intersections, they only lie within the set E. So that's not a problem. And if you are considering complementation, you have to be careful. You are actually taking complements within the set E. So if you take a subset of E, which is of the form A intersection E, you are looking at its complement. The complement is taken within the set E, because E is now the big set that you are going to consider. So try to check that this collection of sets BR intersection E, that will be a sigma field. And with that motivation at hand, we define the Borel sigma field, which we write it as B subscript E, to be the sigma field, this intersection that was obtained from the Borel sets on the real line. Okay, so that is our motivation, and that's what we define. But using some certain notions of topology, it's good to know that you can actually define certain notions of open sets in E. Okay, so there is some notion of topology on subsets. You can talk about that, subspace topology and things like that, but let's not go into it. But if you have a collection of open sets within this sets E, you can talk about generating a sigma field out of it. And what you can actually show is that the collection of all such open sets in E will be the same as the sigma field that was just defined above. Okay, so this in sense matches with the notion of the Borel sigma fields that was originally defined on the real line anyway. So this is good to know that the Borel sigma fields in sense are actually generated by all open sets, but for simplicity we will work with this notion of intersection with the Borel sigma field on the real line, because we know Borel sigma field on the real line very well. We have many explicit sets which we know about, which are in the Borel sigma field. So that's why we will concentrate our attention on Borel sigma field on the real line, and if required we shall go to d-dimensional Euclidean spaces RD, again through this one-dimensional ideas, multiplying the sets appropriately, or we will go to subsets E, or we will go to the extended real line. Okay, but just to comment, this identification that the open sets in E will generate the same sigma field as that intersection with the Borel sigma field on the real line, that again will require an argument involving this principle of good sets that was mentioned earlier in note 22. Again, just to repeat, this is the general technical result, and again due to time constraints we are not going to discuss this. Take this as a fact that this can be done. Okay, so we stop the lecture here.